All right, welcome back. We're going to go ahead and start on some examples here. Okay, so this is example 8.1. We're calculating momentum here. So the first part asks to calculate the momentum of a 110 kilogram football player. So mass is 110 kilograms. And he is running at 8 meters per second. Okay, so we want to calculate the momentum. Remember that momentum is mass times velocity. So this would be 110 kilograms times 8 meters per second. Okay, so we can plug that into our calculator and we should get 880 kilograms meters per second. Okay, so that is the momentum of that football player. Now we want to know, we want to compare that momentum to the momentum of a thrown football. Okay, so the mass of the football is 0.41 kilograms, and it's thrown at a speed of 25 meters per second. Okay, so we have 0.41 kilograms times our velocity, and that is going to be 0.41 times 25. We get 10.3 kilograms meters per second. Okay, and if we're trying to compare the two, you can say that's P1 and this is P2. P1 over P2, you can say 880 over 10.3. It's about 85.9. So this means that the momentum of the football player is about 85 to 86 times greater than the momentum of the football itself. Okay? All right, so, whoops. We move on here. I don't know, my screen is glitching yet again. We're now going to be calculating a force. Okay, so this problem basically states that there was a record of a speed, which is 58 meters per second. And we want to know the average force exerted on a tennis ball, which has a mass of 0.057 kilograms. Okay, assuming that the ball's speed just after impact is that 58 meters per second. Okay, that the initial horizontal component of the velocity before impact is negligible, and the ball remained in contact with the racket for this amount of time, 5.0 milliseconds. Okay? Give me 1 second while I try to figure out what is going on with my computer. Okay, so we have some amount of time here, and that was given to us in milliseconds, and we're going to obviously need that in seconds. So let's go ahead and convert. There are 1,000 milliseconds in 1 second. Okay, so 5 divided by 1,000 is just going to be 0.005. 0.005 seconds. Okay, so again, we're trying to find our force. So we defined our net force as being our change in momentum over some change in time. Okay, and our momentum, if you remember, is going to be our mass times velocity. Okay, so we can go ahead and plug these things in. Our mass is 0.057, whoops, 7 kilograms times our velocity, which is 58 meters per second, divided by our time, which is going to be 0.005 seconds. Okay, so we have 0.057 times 58 divided by 0.005. And we get our force is 661 newtons. Let's make sure that our units are correct. Okay, so we have a kilogram meters per second over second, which is kilogram meters per second squared, which is 1 Newton. So good. So our units are correct. Okay. All right, so that was that second example, not too bad. Okay, let's move on. So this one, we are going to be looking at billiard balls, okay? And we have 2 of them. They're traveling at the same speed, and they're reflected without any change of speed. Okay, so let's see. We have 2 billiard balls. 2 billiard balls strike a rigid wall with the same speed. They're reflected at the same speed. Okay, first ball strikes perpendicular to the ball. Oh, I see. Okay, so the first ball strikes perpendicular to the wall, which is like that. Okay, the second one, let's see, let me put a little line here, strikes at the wall at an angle of 30 degrees from the perpendicular. So let's go ahead and say that that's 30 degrees here. Okay. So that's where that ball is coming in. Okay. It's going to be 30 degrees. And bounces off at an angle of 30 degrees from perpendicular to the wall as well. So it hits that way, and then it'll bounce off whoops, there we go, at 30 degrees as well. Okay. All right, so the first part says determine the direction of the force on the wall due to each ball. Okay, determine the direction of the force on the wall due to each ball. Okay, I'll give you guys a second to think about that one. Okay, so hopefully that was some time to think. You could pause the video as well if you want to think about it some more. But looking at our first mass here, or our first ball, I should say, the ball is hitting straight towards the wall. Okay, so that means that our force that our wall is putting a force on the ball is going to be in the opposite direction that it was hit. So we have our ball comes in and it hits directly here and it bounces back. Okay, so this means that our F, or our force for this first one, is in the negative X direction. Okay. Now, for the second one, it seems a little tricky, but it's not as it seems. So if we have our billiard ball going towards the wall at some angle here, okay, and it hits, our force is still going to be in our negative X direction, okay? It's still opposing in that direction, okay? So that is part A, okay? Now we want to calculate the ratio of the magnitudes of impulses on the wall, or I'm sorry, on the two balls by the wall, okay? So we remember that impulse was the change in momentum. So it is the F net times time, okay? And if we are looking at the ratio of magnitudes, we can ignore time, because if this is the first one divided by the second one, the times don't really matter, okay? So we will need to figure out the impulses of both of them. Okay, so F net 1 and F net 2, okay? All right, so in this case, we can just focus on this side of the impulse equation. We don't really need to worry about the time or calculating the F net exactly. So let's go ahead and do that. Okay, so let's erase this. Let's make it a little nicer. So we know that impulse is our change in momentum. Okay, so we want to know for the first case, what is the change in momentum? And then for the second case, what is the change in momentum? Okay, so for the first one, our change in momentum is purely in the X direction, right? We don't have any kind of Y direction here that's changing. It is just straight on the X axis, right? Okay, so this is X and this is Y. Okay, so we should have some P final minus P initial, okay? And it's only on the X axis or direction. So we have our mass times our velocity final minus our mass times our velocity initial, okay? Now, reading a bit closer, our speeds don't change, but our velocity direction will. Okay, so remember that these are vectors. Should put that on there. Okay, so our velocity here, our initial velocity is going to be the same as our final velocity, but they are changing in direction. Okay, so the first one, it's going in a positive X direction, right? So that's V initial. Okay, so that's going to be, write it over here, VI. And that's going to be in the positive direction, so it'll still have that minus sign out there. Our second one, though, our second final velocity is in the opposite direction. It's now in the negative v direction. Oops, I should erase that. Okay, so our delta p here is going to be minus 2mv. And again, that's all in the x direction. Okay, so let's go ahead and look at our second case. So we will have our x direction and a y direction here. Okay. Okay. So when we're looking at our second case here, we want to know about our initial and our final. So let me go ahead and write that out. So we're going to have some mass times our V final minus mass times V initial. Okay. And again, all in the x direction. So I'm going to skip that and then mass. Okay. So initially, looking at our diagram here, we have our V initial coming in, okay, at some angle. So let's go ahead and use some trig to figure out our x value here. So that's going to be adjacent, okay, and if you notice, remember that this is the positive x, this would be the negative x. So this is going to be a negative value, okay, so it's going to be negative. And we're looking at adjacent, so it's going to be cosine, okay? So it's going to be V cosine of theta. I'm just going to say theta, okay? All right, and then for our final, it's going to be again adjacent, right, over the final. So it'll be, again, a minus V cosine theta, okay? Okay, I just noticed a quick mistake here. My initial velocity is in the positive x direction, not the negative direction, right? Because it's going in the positive direction, okay? And my final is going in the negative direction, so that one's okay. Okay, so we end up with a negative 2mv cosine theta. Okay, oops. So that is in our x direction. That's our impulse in the x direction. Now for our y direction, we have our mass times velocity final minus mass, oops, velocity initial. Okay. So for our final, we have opposite, okay, over hypotenuse. That's going to give us sine, and that's going to be a, let's see, positive V sine theta, okay, minus our initial, which is going to be, let's see, opposite again. So it's going to be V sine theta. And it is still going in the positive y direction, so we'll put a little plus sign, okay? And so this term minus this term is just 0. Okay, so there is no change in momentum in our y direction here. Okay, so if we want to compare these two, so compare, it's just going to be in the x direction. And we can say our impulse for our first one divided by our impulse of our second one is going to be minus 2mv over minus 2mv cosine theta, okay? Which is just going to end up being 1 over cosine theta. And our theta is 30 degrees. So we can go ahead and plug that in. So then 1 over cosine of 30 degrees is 1.15. Okay. So our impulse of our first, the impulse of our first scenario is 1.15 times the amount of the impulse in our second scenario. Okay, so this impulse is higher than this impulse. Okay. All right, so I'm going to stop here and then I'll continue in another video with more examples.